Hi, and welcome to week one of Science 137, Introduction to Meteorology. We're going to go over some radiation basics, because those were brought up in the forum, and a little bit about the greenhouse effect. This is October 2013. We'll probably reuse parts of this for future classes, but we'll address these questions right now. So to start, first of all, some background. We're going to rush through and not do a lot of the math that maybe earth sciences majors or meteorology majors would have to do. We don't have to do the math in this class, but there is a lot of math to be done, and we're going to race through it. So if you want to actually go through the details of how to calculate the numbers that I'm going to be spitting out, that's in your textbook. And that's available in a large variety of lectures out there. Or you can send me an email and I'll get you some materials. But we're going to basically deal with this at the conceptual level, and we're not going to be cranking through mathematics. Another thing is we're going to treat the sun, we're only going to consider two bodies. The sun, which is big and hot, and the earth, which is cool and not. And the Earth is, on average, 93 million miles from the sun. So that'll become important in a second. But we're not going to consider the fact that the Earth's orbit isn't perfectly circular, and that the Earth isn't a perfect sphere, and that the sun actually has a tiny up and down pattern to its output. We're going to consider the averages. The sun, on average, is this temperature. The Earth, on average, is 93 million miles from the sun. The Earth on average is so many kilometers in diameter. So we're kind of treating this thing by the averages. Okay, so let's talk about radiation and the difference between ultraviolet and infrared and visible light, and where we're coming from on all that. So the first thing to know is radiation, for the purposes of this course and especially this chapter, that doesn't necessarily mean the scary stuff that can make you sick. Radiation in this book or in this course is a broader concept that basically means the electromagnetic energy or the electromagnetic waves that are given off or radiated by any object with a temperature. So radiation is basically, you can think of as light and other forms of electromagnetic energy that something gives off. And this can be gamma rays, X-rays, microwaves, radio waves, whatever. Those are all forms, or those are all different frequencies of electromagnetic waves or energy. But we're going to zoom in for the purposes, we're going to forget about all of those. We're going to zoom in on visible light, the piece of that frequency spectrum that we can see, and then its two neighbors, a lower energy, lower frequency neighbor called infrared, and a higher energy, higher frequency neighbor called ultraviolet. So that's what we're going to concern ourselves with for this course, or this chapter especially. So radiation. So things that have a temperature give off radiation that is characteristic of that temperature, and that includes us. Night vision goggles are tuned to see the frequency of light that we give off by the fact that we're about 99 degrees Fahrenheit. We give off infrared light because we're about 99 degrees Fahrenheit. We actually glow with light. We can't see that light with our eyeballs, so we use night vision goggles because they are artificial eyeballs that are tuned to see the frequencies at which we glow, which happens to be a lower energy, lower frequency than visible light, which is what a lot hotter things give off. We can actually see that. We can see that in a campfire. We get that wood oxidizing and burning hot enough, and it glows, and it gives off light, in addition to a lot of infrared energy as well. The sun, being several thousand degrees warmer than the Earth, gives off a lot more energy than the Earth, and that's an important concept. So the temperature of an object has everything to do with radiation, in a sense that a warmer object gives off more energy, larger output, more radiation than a cooler object. And a temperature, a warmer object, also the warmer an object is, the higher frequency that object gives off as its dominant form of energy. So to take that gobbledygook and try to turn it into English, the sun, a lot warmer than the Earth. So every square inch or square foot or square meter of the sun is going to give off a whole heck of a lot more radiation, electromagnetic energy, than every square inch or square foot or square meter of the Earth does. The sun is also going to give off that energy. It's going to be dominated in the part of the spectrum that is visible light, which is a much higher frequency or energy than infrared radiation, relatively speaking. So the sun, by the nature of the fact that it's very hot, we all kind of instinctively know, wow, something that is that bright has got to be hot. But what we're kind of glossing over, and when we think about that, is something that glows white hot like the sun. It is very hot, and we do experience that. We don't go touching things that are glowing white hot. But what is really happening there is the temperature of that object is so much warmer that it's emitting energy in the visible spectrum, which is a lot higher energy than the infrared spectrum that even warm-blooded mammals like us give off. So it's giving off its energy in frequencies that our eyeballs can perceive as light. Does that make sense? I hope it does. So zooming in on the electromagnetic spectrum, there's gamma rays and X-rays and microwaves all over the place on either side of this, but we're zoomed into the area around visible light. So these are the frequencies of light that we can see. The different colors that we can see are sorted through this visible spectrum. And we get lower energy off to your right and higher energy, higher frequency off to your left. And we happen to call infrared, less than red or within red, these are the types of light that are slightly lower frequency than red, which is the lowest frequency of light that we can perceive with our eyeballs. Ultraviolet means more than violet or bigger than violet. That's basically higher frequency waves than the blues and purples, which are the highest visible light that we can see. So when we talk about infrared and visible light and ultraviolet light, we call them all light because they're on the part of the electromagnetic spectrum where visible light is, and they're just different frequencies. And I hope I can do this right the first time. But the sun is again several thousand degrees warmer than the Earth, and the nature of its output is that it's so warm that its maximum output kind of falls in the visible light range, which makes sense to us. We see it every day when we face it. It gives off a lot of visible light. And the Earth, being much smaller, or much cooler, sorry, it is smaller, gives off, and we're in the blue there, a lot less energy than the sun, and we peak in the infrared. In fact, almost all of the energy that we emit from the Earth is in the infrared, because we're cooler than the sun. Again, the shapes of these are probably not exact, and a radiation professor would criticize the simplicity of all this. But the difference between infrared, ultraviolet, visible, and infrared is basically, for the purposes of this chapter, these are frequencies that are given off by objects of different temperatures. So you asked about ultraviolet, and ultraviolet light happens to be harmful to a lot of living things on our planet, and the sun does give off, although it gives off a lot of visible light, it also gives off some ultraviolet light that comes to our planet as well. So thankfully, the ozone layer in the stratosphere does a great job of filtering out or capturing, collecting a lot of this ultraviolet radiation that's coming from the sun. So this is where the ozone hole, if you're a child of the 80s and 90s, you remember a lot of talk about the ozone hole and ozone depletion and ozone depleting substances, and this is why we use a different type of refrigerant than we used to, because ozone, especially in the stratosphere, is good at kind of blocking or filtering these wavelengths that come through. Not related in any large part to climate change or global warming. The ozone hole is a separate issue. The ozone has to do with the filtering and the interception of ultraviolet light. Ozone, just by the way it is, just its nature is, it tends to absorb ultraviolet radiation before it reaches the surface. And when we we lower the concentration of ozone in the stratosphere, we are exposed to more ultraviolet light that comes through and can damage our tissue and our skin and many of the things that we do. So that's why that was important. But it's not, it's only very, very, very tangentially related to climate change or global warming. It's kind of a separate issue. Anyway, so the things to get from this, again, higher energy to lower energy or lower frequency waves. Sun is hot, it gives off more radiation at all wavelengths than the Earth, but it happens to be centered in the visible range, which is why we've developed eyes that can see visible light. The Earth, a lot cooler, and we emit in the infrared range. So infrared is a light that is a lower frequency or lower energy than the visible spectrum. It is, although our eyes can't see it, our skin can feel it. When you make a campfire or a bonfire and you get that hot, it's emitting some visible light, but it's actually emitting a whole heck of a lot of infrared radiation as well. And so if you stand next to your campfire, if you stand, say, 20 feet from a big bonfire, and you face that bonfire the whole time, and the front of you feels really warm, and the back of you is not, it's because the front of you is intercepting a lot of that infrared radiation, and you're getting warm because of it. That's why you kind of do that little dance where you turn away from the campfire for a while, and then you turn your front to it, you turn your back to it. But that campfire's temperature is probably somewhere in here, it's a few hundred degrees warmer than us, but not a few thousand degrees warmer than us. So it's giving off some reddish, yellowish, orangish light and a lot of infrared radiation. So anyway, that is that. Cooler, relative to the sun, cooler objects are going to give off less radiation, and they're going to give off radiation at frequencies or wavelengths that are lower frequency. So that's that. All right, finally, the greenhouse effect. The Earth is a ball in space, and it is 93 million miles from the sun, and the sun giving off a relatively constant amount of energy based on its really hot temperature. The Earth is a certain size, and we're basically a ball out there in space, and we collect that incoming energy from the sun, and because we are at equilibrium, we also give off the same amount of energy in the form of infrared radiation. So if the Earth didn't have an atmosphere, it turns out if you do the math on what an object this big that is a ball 93 million miles from the sun, if we didn't have an atmosphere, the Earth's surface would be about 0 degrees Fahrenheit, give or take a degree or two. So obviously that's not what we are. So the fact that we have an atmosphere makes a difference in our surface temperature. And here's how it does it. We talked a lot about the difference between ultraviolet and visible and infrared radiation. And it turns out that the gases that make up our atmosphere, mainly nitrogen with a lot of oxygen, some water vapor, a little bit of carbon dioxide, some argon, some trace gases, turns out that composition of our natural atmosphere, at least our recent natural atmosphere, is really transparent in a relative sense to the visible frequencies. So the visible light that the sun gives off makes its way through the atmosphere pretty much unmolested, unless it hits a cloud and bounces off. So a great deal of the visible light, as long as it's not reflected back into space by clouds, makes it through the atmosphere and strikes the surface. So the atmosphere is really transparent to visible light. It's why you can see on a clear day without a lot of dust and raindrops in the air, you can see a long way, because the visible light waves that the atmosphere is pretty transparent. Turns out that those same gases are less transparent, especially in the infrared. So what happens is the radiation that comes in from the sun to the atmosphere largely makes it to the surface of the Earth. But the Earth emits radiation in the infrared because it's a lot cooler. It is of a temperature where it is giving back that energy to space in the infrared. And that very thin atmosphere that we have actually picks off a lot of those infrared frequencies. The way that the molecules are, the different gases in the atmosphere, they basically absorb radiation at various frequencies in the infrared, and when it does that, it prevents that radiation from making it back into space. We'll go over this in the climate chapter, but what actually happens is it receives the energy, it absorbs it, it re-emits it, and so essentially the net result of all of that is, because the natural atmosphere collects some of that outgoing infrared energy and re-emits it, a lot of that re-emission goes back to the surface. And so what we're doing essentially is re-warming the surface of the Earth at the expense of the higher atmosphere. And that's what the greenhouse effect is. It's not just everything that goes in comes out. It's everything that goes in comes out. Some of it's captured in the atmosphere and sent back, and then some of that's captured in the atmosphere and sent back. And so the net result is we have a net warming of the lower part of the atmosphere at the expense of the upper part of the atmosphere. And eventually, when all of that stuff comes to equilibrium, we have a planet that is roughly 58 degrees Fahrenheit, give or take a few, rather than 0 degrees Fahrenheit. So the natural atmosphere itself, the greenhouse properties, the fact that the constituents of the atmosphere, nitrogen, oxygen, carbon dioxide, water vapor, argon, trace gases, the fact that they can absorb and retransmit, kind of recycle some of that outgoing infrared energy, that makes us a warmer planet than we would be without an atmosphere. It is called the greenhouse effect, and it's a different process, but the result is the same. The fact that there's some kind of blanket up here is trapping some of the energy closer to the surface before it makes it all the way out. So that is the greenhouse effect in general. It's because we have a warmer surface of the Earth than we would have without an atmosphere, because that atmosphere, which is transparent to visible light, which is a big percentage of what the sun puts out, is not as transparent to infrared light, which is what the Earth puts out. And so the relationship between this and global warming is carbon dioxide and several other greenhouse gases. When we increase the concentration of those greenhouse gases, we're essentially tweaking that process up. We're capturing more and more infrared energy before it goes out into space, and we're warming the surface of the Earth as a result. And there's a whole bunch of different greenhouse gases. The reason that carbon dioxide is kind of the biggie, the one that everyone worries about, is it's a really stable gas, and it stays in the atmosphere for hundreds, if not more than 1,000 years before kind of breaking down chemically. So it's not necessarily the most potent greenhouse gas. It's just there's a lot of it, and it lasts for centuries. And that's why carbon dioxide is kind of the greenhouse gas. Methane is actually more potent, kind of pound for pound, in its kind of greenhouse quotient, or its ability to trap more heat. But there's not as much of it, and it lasts decades rather than many centuries. But it's becoming a more and more kind of a bigger concern in the climate change area. But we'll get into all that in Chapter 7. The important thing is the greenhouse effect is a natural effect. It is, even without all the global warming stuff, it is something that happens, that our atmosphere does to keep the surface of the Earth warmer than it would be without an atmosphere. And it's because the atmosphere is transparent to visible light, which is what the sun largely gives us, but it's not as transparent to infrared light, which is what we're trying to give back to space. And the increased greenhouse effect, or greenhouse gases, or global warming, have to do with increasing certain gases that are long-lived and enhance this effect. And that's where we're going. Hope that helps. This is a really long video. Best of luck to you for the rest of this semester. And thank you for your service. I really appreciate those of you who are overseas and deployed, and I know many of us back here in the States do as well. For those of you who are here in the States, thank you also for your service. You're an important part of everything that happens.